So let me define kmfun, that is keymap function, as a pointer to a function that takes a car and returns int. But instead of being a variable, I want kmfun to be a typedef. So I just stick the word typedef in front of what would otherwise be a variable declaration. And now this dramatically simplifies the declarations of my keymap arrays. Okay, I can say ins keymap is an array of 128 kmfuns. That is, ins keymap is an array of 128 keymap functions. Because of my typedef, that is exactly equivalent to what I wrote before, which was that ins keymap is an array of 128 pointers to functions that take care and return int. Now, there's a philosophical discussion that one can have about whether typedef improves the understanding of what's going on or postpones the understanding of what's going on. Even if you define kmfun correctly as a typedef and use kmfun to declare variables or arrays of keymap function pointers, you still have to know that that thing is a pointer to a function that takes a char and returns an int, or you will not be able to use the function properly. Okay, so typedef is very useful, but it's not magic and it does not replace needing to know what's going on. Size t is an example of a typedef defined by your compiler for you. Size t is guaranteed to be some unsigned integer type. But whether it's defined as unsigned or unsigned long or unsigned long is a decision made by your compiler developer. In your code, you simply use the name size t to contain the result of the size of operator or to contain the return value of object size and length functions. But you should not make assumptions about whether size t is a 32-bit value or a 64-bit value or some other size of value. The suffix _t is used frequently in the library to indicate that some word is a data type name defined using typedef. Now we're going to take a look at more uses of const in your C++ code, especially with regard to classes and data and member functions. We've used const in two ways so far. One way is to use const to specify that a quote variable unquote is a constant whose value cannot be changed. For example, in this statement, we're declaring pi as a double const initialized with 3.14159, etc. So pi will be a double initialized with the value that we've specified, and the value of pi cannot be changed through the action of your code. The second thing that we've used const for is with respect to references or pointers to things to indicate that the referred to object or the pointed to object cannot be changed. So here we have an overloading of the ostream insert operator or put to operator, which takes an ostream reference as the left argument and a reference to an employee const as the right-hand argument. And the const means that this function promises that it will not change anything about the employee that's been passed in as the second argument. Now, it's easy when talking about consts to become confused by terminology. Before the const keyword was introduced, the terminology was easy. You could have variables containing values, such as this double variable named pi that we've initialized with 3.14159, etc. And if you wanted to make sure that a value couldn't be changed, you would create something called a defined constant using this #define preprocessor directive. #define would cause some token, in this case the token P I, to be replaced in your code with some other text, in this case the text 3.14159, etc. Now, the advantage of the variable, of course, is that you can change the variable. The advantage of the constant is that you can't change the constant. However, the constant created using pound-define is annoying because it's handled by the preprocessor rather than by the compiler itself. And so, if you have a compiled program that you're attempting to debug, this token, pi, in caps, is not found in the object code of your compiled program because it's treated as a text substitution before the actual compiler runs to produce object code. So this is a nuisance, and one of the reasons why the const keyword was introduced. But on the other hand, when the const keyword was introduced, this created some confusion about terminology, because now we have a variable, as we had before. Pi here is a variable of type double, initialized with 3.14, etc. And we have two kinds of constants. We have the pound-define constants, and we have the const constants. And people were confused about what to call these things. Are these const variables? What does it mean to talk about a const variable? So the terminology that was eventually worked out was that pi here, in the example at the top of slide 17, is referred to as a symbolic variable, meaning it is a variable, it occupies memory, and it has a symbol associated with it that you can see in the symbol table if you're using a debugger. All right, so that symbol pi is available for a debugger to look at. Then we have what's called a manifest constant, which is the pound-define version. The token pi here is a constant which is simply textually replaced throughout your source code with 3.14159, etc. But it's not symbolic. That is, the symbol, capital P, capital I, is not going to be visible from within a debugger. And then if you use const, on the other hand, you get what is called a symbolic constant. That is, it's constant in the sense that its value cannot be changed. It's symbolic in that that symbol, capital P, little I, is going to be visible if you run a debugger on this compiled program. So here on slide 18, we have a brief description of the meanings of these terms, symbolic versus manifest, and variable versus constant. I'm not going to require you to remember these definitions, but you might hear people use these terms. Next, we're going to take a look at what are called const member functions. Now, you may recall, but you probably don't, since this was last year after all, that when we defined the insert operator for our binary tree class, the right-hand argument that we passed to the insert operator was specified as a reference to a binary tree. Now, the insert operator is not going to change that binary tree, so it's worth asking, why didn't we declare that parameter as a reference to a binary tree const? The picky technical reason why we didn't do that is that in the implementation of this insert operator, we invoked another member function, put2ostream, on that argument binary tree object. And in order for us to be able to invoke put2ostream on this binary tree object, the compiler has to have some way of knowing that put2ostream will not change the binary tree object. And there's nothing about how we wrote put2ostream that tells the compiler that put2ostream will not change the current object. So how do we tell the compiler that a particular member function like put2ostream is not going to change the current object? Now, it's tempting to say, well, who cares? This function works fine. We know that we're not changing the binary tree object bt, so why should we bother fussing around with const? Well, let's take a look at this main function over here on slide 20, written by some application developer who is perhaps someone other than us. We, as the developers of a class, have no way of preventing an application developer from declaring any object that they want to be const. For example, here we have a non-const binary tree object bt1,